I am Naeem and today we will solve this my 2022 paper AS Chemistry 9701. Okay, the question number 1 is, so this question from atomic structure I think, and figure 1.1 show how first ionization energy vary across period number 2. So we have these elements and they are belonging from period number 2. The first question is construct an equation to represent the first ionization energy of oxygen, include state symbols. First ionization energy mean it is minimum amount of energy required to remove electron from independent gaseous atom. Okay. For example, now we have this oxygen. I will write this oxygen here. Okay. So no need to write oxygen molecule because it is energy which is like required to remove electron from atom, independent gaseous atom. Oxygen atom exists in the gaseous state. Okay. So now you are removing electron is valence shell. So now you are actually removing the electron and this oxygen atom will convert into oxygen positive ion into gaseous state. Okay. So the next question is state and explain the general trend in first ionization energies across period 2. So we can notice it generally it is increasing. Okay. From left to right it is increasing. So why it is increasing? We know like atomic number of this lithium is 3, barium is 4, boron is 5, carbon is 6, 7, 8, 9, and 10. So we know down from left to right, atomic number is increasing. Okay. So generally, ionization energy increase. Okay. Left to right. Okay. So number 1 point for this information. Now we have 3 mark questions. So we need to write 2 other points. So then left to right, proton number is increasing. Proton number increase left to right. Proton number increase left to right. That is why, okay, that's why, like the forces of attraction between nucleus and valence electrons increase. Okay, so it is the reason like forces of attraction between nucleus and valence electrons increase. Even you can write this like the size of an atom. Okay, left to right, size of atom decrease. Okay, atomic radius, even you can say size of atoms decrease. Okay, left to right. Okay, even you can say like atomic radius of atom decrease from left to right. Okay, explain why ionization energy A in figure 1.1 doesn't follow the general trend in first ionization energies across period 2. So he is explaining energy of A. Okay, and you can see here we have this A and it is an oxygen. Okay, if you see the electronic configuration of this nitrogen and oxygen, we have this nitrogen. The atomic number of oxygen is 7 and MR is 14. Okay, so there are 7 electrons. So it is 1s2 and 2s2, 2px, 2py, and here we will have 2pz. Okay, so there are 7 electrons, 1, 2, 4, 5, 6, and 7 electrons. Okay, So now you people can see there are 7 electrons, and if we draw the structure of this oxygen and atomic number this oxygen and A, it is 8, and it will become 1s2, like 2 electrons, then 2s2. Now we will have this 2px, 2py, and 2pz. Okay. So there are 8 electrons, 2 to 4, 5, 6, and 7. So remaining one 8 one is here. Okay. So they actually it is number of electron and they are showing the opposite spin. Electrons are spinning opposite to each other. Okay. So you can notice in nitrogen electrons are in like they are unpaired form. Okay. But here we can say one of the pair is a paired. Okay. So when electrons they spin, there is of course this magnetic field, and now they are repelling each other. It is the reason at this point a low amount of ionization energy is required. But here we can say there is no like electron repulsion. Okay, inner electron repulsion, there is no. So it is the reason more energy required in this case, and here because of this less amount of energy is required. Okay, so we can write the answer. Now general trend. Okay, in A there is inner pair repulsion of 2px electrons. That's why A has lower ionization energy than nitrogen. Okay, it is the reason it is not following that trend. Okay, I hope you people got this point. So now we have the next question. So we have this question next, and in this question element E is in period 3 of the periodic table. The first 8 ionization energy values E are shown. Okay, and now we can see first mean when you remove the first electron, second energy mean when you remove the second electron. Okay, and you people can notice when we are like removing electrons continuously, their energies are increasing. Okay, so deduce the full electronic configuration of E. Explain your answer. Full electronic configuration of E. Okay, so you people can see from here. Okay, when we remove electron, removing your electron from third to the fourth, so you can see there's a very big jump. Okay, here on 2000, here we have 11,000. Okay, so now let me write this electronic configuration till now. So 1s2, 1s2, 2s2, 2p, like 6 electron in the valence shell, maximum. Okay, then 3s2 and 3p1. Okay, so the question is, how do I know this? Like, how do I know? Like, there are 3p. You people can see when you remove the first electron. Okay, when I will remove this, for example, 3p, energy releasing 577. When I will remove second electron from here, 3s. Okay, so there is 1820. But I will remove another from here, so the energy difference will be the 2740. But when I jump from 3s to 2, okay, so there's a big jump. This one, fourth. So when I remove the fourth electron here, so you can notice now I'm close to the nucleus. It is far away from the nucleus, this region. It is the reason I'm expecting like it is from this because the energy gap is a very big. Okay. So what is the explanation? So I can see I can write this statement. Okay, there is a great energy difference between third and fourth ionization energy. Okay. So there's a great. What is the reason? There is a great energy difference between third and fourth ionization energy. Understand? It is the reason. Okay. So you can see like it is having the three electrons. Okay. So the next is the 3 mark question. So it means we can write the other thing. Okay. So we can say it here like the fourth electron removed from a like shell closer to the nucleus. Okay. Fourth electron removed from close orbital of nucleus. Okay. So the next question we have here. Okay. Some oxides of element in period 3 are shown. Metal oxide, it is also a metal oxide. Okay. Phosphorus, non-metal, non-metal, and non-metal. Sodium react with oxygen to form sodium oxide. Sodium is the reducing agent in this reaction. Define reducing agent. It means it is reducing other things, but it is oxidizing itself. Okay. So you can say it is a substance, or even you can say it's a species. Okay. A substance and element are like species. Okay. Which can reduce. Okay. Which can reduce other elements or compounds or compounds, but oxidize itself. Okay. Okay. Write an equation for the reaction sodium oxide. Metal oxides are basic in nature. Okay. So we know metal oxide, sodium oxide, it is basic in nature. When they react with water, they will produce a base. Okay. So now let me write the base, sodium hydroxide. Okay. Understand? So now we need to balance this equation. So you can see here we have Na2 two times. So I'm writing here 2 because now they will become balanced. Okay. So here we have two hydrogens and two hydrogen, one and one, two oxygen and two oxygen. Now write the physics. Sodium oxide exists as a solid in nature. Water exists as a liquid in nature because found in nature as a liquid. Okay. So now product dissolve in water. So it is aqueous. Next question is aluminum oxide, amphoteric oxide found in bauxite. Okay. So please memorize. Three oxides are like amphoteric in your syllabus. Aluminum oxide is amphoteric in nature. Lead oxide is amphoteric in nature. And zinc oxide. Okay, just three in your syllabus. These are amphoteric in nature. So what is meant by the amphoteric? Like amphoteric mean like these oxides, they can react with both acids and bases. Okay, so they are it. They can react with both acids and bases. Okay, so the next question is Aluminum oxide is purified from bauxite. Bauxite is an ore, okay? Aluminum oxide is actually ore, okay? The first step involves using aluminum oxide with an excess of sodium hydroxide. A colorless solution form. Actually, it is the reaction between aluminum oxide and using the sodium hydroxide. So write an equation. So it is actually equation related to, we can say, when aluminum oxide Al2O3 react with sodium hydroxide in the presence of water, because it's soluble in water, must be in water, okay? So then we will get the salt like sodium aluminum. We will get this aluminum hydride, okay, OH 4 times, okay? So now just we need to balance the equation. How can we balance it? So here we will have this aluminum and 3 moles of water and 2 moles of this sodium hydroxide, and we need to put 2 here, okay? Aluminum oxide exists in nature as a solid. Sodium hydroxide also exists as a solid. Water exists as a liquid. Because we are like adding them together in the water, so this will become aqueous condition, okay? Its physical state is aqueous. So we have next question. Aluminum oxide is used as a catalyst in the dehydration of alcohols. State the effect of using aluminum oxide as a catalyst in the dehydration of alcohol. Use the Bose-Band distribution in figure 2.1. Help explain your answer. Here we have this distribution curve, okay? And you people know, like in distribution curve, this area is representing the molecule. They are not making the product, okay? Because energy is increasing left to right, okay? And energy is actually moving left to right. So these molecules, they are great in number, okay? Number of molecule, you can see they are very high in number, but they are not making any product, okay? So use the Boltzmann distribution figure 2.1 to help explain your answer, okay? You know, catalyst speeds up a chemical reaction, okay? Even like I'm writing chemical, speed up a reaction, okay? How? There are number one, point number one, they actually lower the activation energy. Catalyst lowers the activation energy, okay? Activation energy. Number two, change the path of reaction. How catalyst speed up the reaction? Number one, lower the activation energy. Number two, change the path of reaction, okay? What can you be provide a third point? And it like remains unchanged, but it is not effective for answer, okay? So these 2 points you people have to keep in your mind, understand? So the next is phosphorus oxide, P4O6, sorry. It is a white solid that has a melting point of 24 degree, okay? Solid P4O6 react with water to form a phosphoric acid. Deduce the type, structure and bonding. Why? P4O6, explain your answer. So the first point is it is a white solid and has a melting point 24 degrees. So it is a low melting point. So low melting point mean it is not some ionic compound, it is not some giant covalent structure or ionic structure, okay? Because their melting point is low. The first clue is here, okay? And the second one is you can see like it can react with the water. So when things like react with water, so it is type of hydrolysis reaction, okay? So number one point is P4O6 is simple covalent molecule. Why? What is the reason? The reason is number one, first reason is its melting point is low. It has low melting point. Okay. Second point is it is reacting with the water and making phosphoric acid. Okay, so you can say like it is easy to hydrolyze. Okay, so you can see P is non-metal, oxygen is non-metal. When there's a bonding between non-metal and non-metal, they are covalent in structures. But why it is simple covalent? If it is covalent, and for example, if it is making some giant structure, then the melting point should be higher. But you can see the melting point is lower, so it is the reason it's not giant in nature. It is simple covalent molecule. Determine the oxidation number of phosphorus in H3PO3. Okay. Generally, when we write this formula, like normally, H3PO3, phosphoric acid. Generally, we know this phosphoric oxide like this, okay? We can write even then in complexes. But here, how can we find this? You can see we have this H3PO3. You know, hydrogen is from group 1 and the oxidation number of group 1 element is positive 1. But here we have 3 hydrogens and oxidation number of 1 hydrogen is positive 1, okay? So 3 multiplied by 1 will become positive 3. So we need to find the oxidation number of this phosphorus plus it will become X because it is unknown for us. Okay, we need to find out this. Here we have oxygen. Oxygen is from group 6. It contains 6 electrons in the valence shell and now one oxygen atom can gain 2 electrons. So that is why the charge of one oxygen atom is -2. Here we have 3. So they are multiplied with 3 equals to 0. Why I'm writing this 0? Because there is no overall, there is no charge. It's a neutral molecule. That's why I'm writing here minus. So plus 3 plus x minus 3 twos are 6 minus 6 equals to 0. Okay. So how to find the value of x? X will be equal to this negative 6 will move here. It will become positive 6. And this positive 3 move here. It will become negative 3. So our x will be equal to positive 3. So the answer will become positive 3. Okay. So the next question we have, when phosphoric, okay, P4O6 is heated with oxygen, it forms P4O10. Okay. So P4O6 it is being heated in the presence of oxygen and we are getting the product. Overall enthalpy change of total reaction is minus because it is a burning reaction and you know combustion reactions they are exothermic in nature. Okay. The enthalpy change of formation of P4O10 he is talking about it is -3010. Like when we are making 1 mole of this from its elements, so this amount of energy is being released. Calculate the enthalpy change of formation of P4O6. So now we need to find its enthalpy change. Okay. So you people know, for example, we will write it here reactants. I will write it here reactants. And they are converting into the products. And at the lower side, I will write their element states. Okay. I will write their elements. Okay. So now what are your reactants? Reactants are P4O6. You can see it here. Let me draw some line here. Okay. So reactants are P4O6. Sorry. P4O6 plus 2O2 and we are getting this P4O10. P4O10. These are the reactants and it is the product. Now I need to write the elements here because we have these elements. Elements combine together to make reactants. Even when these elements combine together, we will get this product. Whenever you have any like question related to formation, so you need to draw elements like from lower side to upper, okay, low to high, okay. So what are the elements? You can say the first element is phosphorus. I'm writing here P4. Phosphorus exists in nature as a P4 in solid form, okay. Don't forget to mention their physical states. How many oxygens are there in reactants? 6 plus 2, 8. So you people know oxygen exists in O2 form. And how many oxygen? 8. So I will write 4 O2 molecules in gaseous form, okay. So no other element is here, okay. I'm writing this here and I'm writing this like this, okay. So the thing is, okay, P4O6 combined together, so this amount of energy releasing it is minus 1372, okay. So the formation energy of P4O10 is mentioned, it is minus, it is being formed minus 3012. And now we need to find the energy of this, okay. We need to find delta energy of this, okay. So when something is given like in delta H formation, delta H form, okay, he is not talking about bond energies. So when he talk about this delta H of formation, delta H of combustion, so we will use this formula delta H of the reaction of this reaction. It is equals to delta H of products, delta H of minus delta H of reactants. If question is given in like bond energies, then you will use delta H reaction is equal to delta H of reactants minus product. But he is not talking about bond energies, okay? Products minus reactants. So delta H of reaction it is given minus 1372, it is minus 1372 equals to delta H of product. Here we have this product, sorry, here minus 3012. It is minus 3012 minus delta H of reactant. We need to find it delta H of R for reactant, okay. So now bring this minus 3012 this side, it will become minus 1372, negative will become the positive 3012, okay. 3012 is equal to negative delta HR, okay, delta H. So when you will like solve this, I'm writing this answer here because I have a space here, okay. So when minus 1372 plus 3012, we will get the answer positive 1640. Positive 1640. But here you can see we have this negative sign. So your answer will become negative 1640. Okay, so your answer is minus 1640. I hope you people got this question, okay? Write an equation for the reaction of P4O10 with water. So it is from like your, you can say inorganic, and you know when a water like metal, it is non-metal. Non-metal oxides are acidic in nature, okay? So when non-metal oxide react with water, we will get some acid, okay? So P4O10, P4O10, they react with like they are reacting with oxygen, okay? And we will get some acid, okay? Sorry, they are reacting with water, they are not liquid, okay? My bad. Uh-oh, sorry. They're reacting with water, okay. Here we will have this water, H2O, and non-metal oxides are acidic in nature because when they react with water we get some acid, okay. So we are getting acid is phosphoric acid, understand. So it is solid in nature, water is liquid in nature, and it is become aqueous because now it is dissolved in water, okay. So now we can like 4 phosphorus, here we have fun, so I multiply this 4 phosphorus, it becomes stable, okay. So now how many hydrogens are there? 4 is a 12. Here I have only 2. If I multiply this 6 to the 12, okay, so equation is balanced now. Sulfur dioxide and sulfur trioxide are found in the atmosphere. The oxidation of SO2 to SO3 in the atmosphere is catalyzed by NO2. The first step of the catalytic oxidation is shown, okay. Equation 1 we can say SO2 react with NO2 and we're getting SO3 and NO. Construct an equation to show how NO2 is regenerated in this catalytic. It is oxidation to NO. It will again gain an oxygen and become NO2, okay. So for example, we have this nitrogen oxide. They will combine with the oxygen and then we will get this NO2 gas, okay. So their physical state is gaseous and NO, as you know, it is also exists as a gas, okay. But there's a one molecule, so I need to balance for balancing half of the molecule, okay, in molar and molecular form, okay. NO2 can also react with unburned hydrocarbon to form photochemical smog, okay. Photochemical mean those reactions they take place in the presence of light, okay. Smog is actually combination of smog, common in Lahore, Pakistan. Smog is actually made by two words, smoke plus we have fog, okay. So it will become smog, okay, dangerous for health, especially for respiratory system and eyes. State the product of the reaction that contribute to photochemical smog, okay. So from your book, I can even write some general things, but you people should stick to your syllabus, okay. So this is a peroxyacetyl nitrate, peroxyacetyl nitrate. Oh, it is from your book, okay. You can say it's a ratta memorization, okay. It is also you can write pen, peroxyacetyl nitrate, okay. So we are proceeding next. So this question is from equilibrium topic. Okay, figure 2.2 show how the temperature of the atmosphere vary with height from the ground. Okay, so it is the height and temperature is given here. It is a high temperature 20, then lower temperature decreasing. So left to right increasing. Okay. The equilibrium reaction in equation 1 has delta H of minus. It means the forward reaction is exothermic because the sign is negative. So negative sign mean reaction is exothermic. Okay. When when A plus B any reactant combine together and you're getting a product C plus D. So negative mean left to right it is releasing heat. It is exothermic. Okay. Suggest how the position of equilibrium differs at height 20 kilometer. It is at 20-kilometer height and you people can notice at 20 degree here. And if I combine this point, okay, so here we can notice we have minus 55 degrees Celsius. Okay. So position of equilibrium, temperature is very low. Okay, temperature is very low. So when temperature is very low and overall reaction is exothermic, at low temperature, reaction will move towards the right hand side. You will get the more product. Okay. So equilibrium, even you can say at 20, okay, at 20 kilometer. Okay. At 20 kilometer height. Okay. At 20 kilometer height, the equilibrium will shift, okay, will move to the right side, okay. Why? Because at here temperature is low, okay. Reason is temperature is low, okay, due to low temperature. Okay, at 50 degree. So at 50 height, you people can see is, sorry, here. Now you people can notice, okay, it is going down, okay, because now temperature is high. So it is already exo, and by providing high temperature, equilibrium will shift to the left hand side, okay. At 50, at 50 kilometer, okay, so the equilibrium will shift to the left hand side, okay. Equilibrium will shift to the left side because temperature is higher. Temperature is high and forward reaction is exothermic, and forward reaction is exothermic, okay. You know, when temperature is already exothermic, so we cannot increase its temperature, okay. You will get lower amount of product, okay. It will make more reactant, okay. So the next question is, here we have hydrogen halides, okay. HCl, HBr are colorless gases at room temperature. The hydrogen halide can be formed by reacting halogen with hydrogen. Describe, explain the relative reactivity. You know, like if we have this chlorine, then we have this chlorine, then we have this bromine, iodine, okay. You know, electronegativity down the group decrease, okay. Electronegativity decrease down the group, okay. So when electronegativity decrease, their reactivity also decrease. Okay, reactivity also decrease. Reactivity also decrease. Okay. Describe the relative reactivity of halogen down the group when they react when hydrogen to form HCl. You know, down the group reactivity decreases. Okay. And what's the reason? Their electronegativity is also decreased. Okay. So down the group reactivity of hydrogen, okay, halides, okay, of hydrogen halides decrease due to decrease in electronegativity. Hope you people got this point, okay. Down the group real electronegativity actually decreasing, okay. So this is the reason, like down the group there's a like attraction between positive and negative become decreases, okay. Acid is a product of several different reactions. Some of these are shown, okay. SiCl4 react with water, now we are getting HCl. When sodium chloride reaction with I2SO4, so we are getting also this HCl, okay. So write an equation for reaction number 1. So we have SiCl4, we have this SiCl4, or plus we will have this water. Okay, so if you see like in organic chemistry section, you can get this. So you will get this selenium combined with oxygen. So we will get this selenium oxide. Okay, plus the remaining when what we will get this chlorine from here and H from here. You will get this HCl. Okay, so just let me check how many hydrogens are there. Two hydrogens are here. If I put two here, no other hydrogens. Four chlorines are here. Four chlorines balanced now. And now I need to put two here for balancing hydrogens. Okay. Okay, now we have this next question. In reaction to NaCl react with concentrated H2SO4 to form HCl and sodium sulfate, hydrogen sulfate. When sodium bromide react with concentrated sulfuric acid, the products include bromine and SO2. Identify the type of reaction that occur in each case by completing table 3.1. Okay. You know, when sodium chloride react with concentrated H2SO4, you can say it is a type of displacement reaction, or you can say it is an acid-base reaction. Okay. So you can, it is type of, even you can say acid-base reaction, acid-base or displacement. Because when H2SO4 react with NaCl, so we get hydro HCl. Okay. NaBr with concentrated H2SO4, so you can say it is like it is also an acid base because NaCl, NaBr, they both are from the same group. Okay, but what is the problem? You know, down the group, like NaCl, like fluorine, then chlorine. So the above one is oxidizing agent. Okay, so lower one is a weak oxidizing. Yeah, even you can say it is a good reducing agent. It is a weak reducing agent. Okay. So you can say even it is also like acid-base reaction. Even you can say it is a type of redox reaction. Okay. So what's the reason? Because this ion is a strong reducing agent as compared to this. Okay. You can say is a strong agent than Cl negative. You know, like fluorine, chlorine, bromine, and iodine. They are strong oxidizing agents. Okay, fluorine is the strongest oxidizing agent. Then chlorine, then bromine. It is decreasing. Okay, down the group, oxidation ability decrease. But you know, the lower one, they are strong reducing agents. Okay, they are strong oxidizing agents, strong oxidizing, and they are strong reducing agents. Understand? They are weak oxidizing and they are like weak reducing agents. Understand? When heated with the Bunsen burner, HCl doesn't decompose, whereas hydrogen iodide form hydrogen, and you know, it means HCl is a stronger as compared to hydrogen iodide because we know like there's a strong electrostatic. For example, there are strong forces, okay, and here we will have a weak forces, okay. So it even we can write they have a strong bond energy, and they will have a like weak bond energy. Understand? It means HCl will have strong bond energy than this, okay. HCl will have strong bond energy than hydrogen iodide, okay. Because if we see their trend, so left top to bottom, electronegativity decreasing, okay? So bond energy also decreasing down the group. So now we have next question. So this reaction is from, I think, organic chemistry, one of my favorite. The hydrogen halide dissolve in water to form strong Bronsted Lowry acids. The concentration of strong acid can be determined by titration. State what is meant by strong Bronsted Lowry acid. You know, a strong acid mean like which ionize completely, okay? And because it is a like Lowry Bronsted acid, you know, Lowry Bronsted acid they actually donate. Lowry Bronsted acid they donate H positive ions. So you can say they donate H positive ions completely. So 1 point for donation of H positive ion, second point for completely. If they are weak, so then you will write they donate H positive ions like partially. Okay. So the next question we have this 3.2 sketch the pH titration curve of produced okay when 0.1 mole it is a concentration mole per dm cube. Okay. My name is Naeem and it is Naeem is equal to vice chancellor. Understand? So what is the concentration? So we will divide here. So concentration is mole per dm cube. V is actually volume in decimeter cube. Okay. N is equal to mole. And what is the volume? It is in decimeter cube. Okay. So dm cube is actually in your life. Dm cube is equal to 1 liter. Okay. 1 liter. Understand? So same concentration mole per dm cube of NaOH added to 25. Say this it is the volume of 0.1 mole dm cube HBr. It is the concentration of other HBr. Okay. And here we have same concentration of this ammonia added to 25 cm cube of this HBr. So these two things are same. But you know NaOH is a strong base, ammonia is a weak base. Okay. So now we have to draw there. So the volume is given. It is 25 degree. So the volume is 25 degree. So here I will have this 25 degree. Okay. The volume. And here I will have this volume 25. Sorry, not degree, centimeter cube. Okay. So it is a strong base. Strong base mean its pH is around 12, 13, 14. Okay. So I need to bring their curve because it is a strong base till 12, 13 or 14. Okay. So how I can draw this, you know, like I'm like increasing the volume. And while I'm increasing the volume, you know, I need to bring this volume at 25. Okay. So now it is going up. It is going up until you bring it here till 12, 13 or 14. I am bringing it here till here like 13 and now I am like changing its direction from here to here. What is the reason? Because it is a strong base and its pH should must be around this 12, 13 or 14. Okay. So here you can say 6 and 7. You people can see at this point it is known as end point or even you can say it's the Aquilus point. This point is representing which concentration of H ion equals to concentration of OH. Like when it is a solution is your neutral at this pH 7. Okay. So what about this? We are using this ammonia and you know ammonia is a weak base. Okay. So weak base means its pH is around 10, maximum 11 or lower than 10. Okay. So now I need to like draw this volume change. Okay. So to the initial volume I can use it from here 0.1 mole dm cube. Okay. Like 1 mole 0.1 in per dm cube. Okay. So that is why I need to bring start from here. So I am bringing from here. But I will bring it here because it is a weak base, so I'm not moving above, okay? Because it is a weak base, understand? So once again, this point is a neutral point, okay? Equivalence point, this point, understand? So I think I made a mistake from here, so I should start this from here, not from here, okay? This from here, okay? So next question is, It is from organic. Sorry, previous one was not from organic. That was from equilibrium acid base. So HBr react with propene to form bromoalkane, and this okay, it is secondary or tertiary. Okay. Complete a diagram to show the mechanism of reaction HBr to propene to form the major organic product. Okay. So now we have it is alkene. Alkene means there's a double bond and electron density of pi electrons is higher. Okay. And what about this? You can say it is a partial negative charge because it is halogen. Group 7 member it is electronegative and hydrogen is electropositive. Okay, because bromine is like pulling the electron of this hydrogen. It is become some electrophile. Electrophile mean electron deficient. Okay. So this pi electrons, high electron density, work as a nucleophile and they will attack over this hydrogen. And now this electron pair, electron of this hydrogen and bromine, they are moving towards this bromine. Okay. So now we will get the CH3, this carbon, and like this positive part will attach on the carbon which will have more number of hydrogens. So you can see this carbon has two hydrogens while this carbon is connected with one hydrogen only. So the positive end of your this like reactant, it will attach to which carbon which have more number of hydrogens. So hydrogen will attach on this carbon. Okay, I am drawing this carbon and it is the hydrogen which is coming from here. Okay, okay, and its own hydrogens are here. And now you people can see this carbon is making how many bonds it is making? It is making three bonds. One with this carbon, other because first there was a pi bond, but there's no more pi bond. So it will become a carbocation. It is a secondary carbocation. Why? This carbon is connected with this and this carbon. When a carbon direct connected with two other carbons, this carbon is known as secondary. Okay. So it is a carbocation, so it is a secondary. So now this Br negative Br negative act as a nucleophile rich of electron. It will attack over here and you will get the final product. You will get this CH3 with this C, with this hydrogen, with this Br and with this CH3. Okay, it is your major product, prominent product because your carbocation was tertiary. Okay, suppose if I have this structure, carbon with this hydrogen, hydrogen and with this hydrogen. Okay, so if it is another carbon with this hydrogen, double bond with this CH2. Suppose this HBr, it is attacking over this hydrogen, bond is broken down. For example, I am attaching this hydrogen with this carbon now. Okay, I am like making opposite product of this. So you can say CH3, CH3. I am attaching this carbon with this, and this carbon will like this hydrogen and this hydrogen. You can see two hydrogens, one and two, one and two. Now this carbon will become a carbocation. Here we can see, here we have this primary carbocation, okay, and primary carbocation is less stable than this secondary. So Br negative, it will attack over here and you will get the product, okay. So it is the primary carbocation, it is your less product. Here we have this secondary carbocation, so it is your major product, okay. It's the more stable. Secondary carbocation is more stable than primary, okay. Why the two bromoalkanes are not produced an equal amount by this reaction, okay? Because in reaction 1 you can say, okay, secondary carbocation is more stable, secondary, sorry, here. So secondary carbocation, carbocation is more stable than primary carbocation, okay, carbocation. That's why we are getting this major product and we are getting this a minor product, okay. You can write this answer according to this, okay. The reaction of CH3CO2, Br and OH is different depending on whether water ethanol is used, okay. So we know when we have any halogen alkane, okay, when you have this halogen alkane and you react this halogen alkane with base, if you are reacting with water, it will follow the elimination, sorry, it will follow the nucleophilic substitution reaction. But when alcohol is a solvent, it will follow the elimination, okay. So when we are using this water, in the presence of water, so we will get this water like Ca3, CH2, CH2 and OH. So what is the inorganic product? Sodium bromide, okay, NaBr. And when we use ethanol, so it is a condition, we will get some elimination product. Ca3, CH and double bond CH2, okay. So let me explain this for you guys, okay. So for example, I'm having this, okay. Ca3, CH2, I'm having this Ca3, CH2 and this CH2 and it is bonded with Br, okay. If I'm using this a base you know is a OH negative, okay. Even you can say Na positive, OH negative. In aqueous condition, water is being used solvent, okay. So you know this OH negative is a base, it will attack over this carbon is electrophilic positive carbon, Br is electrophilic negative, okay. So Br will remove from here, so you will get this, it is a nucleophilic substitution reaction, Ci3, CH2, Ci2, and now this Br is removing and OH attached here will become alcohol plus this Na and this Br, you will get inorganic product NaBr, okay. So other side of the reaction is if you're using this NaOH, a base, but now condition is alcoholic, okay. In alcoholic condition, the reaction will follow elimination reaction, okay. So what is actually elimination reaction? I'm writing it here, Ca3, CH2, CH2 attached with the Br, okay. So let me write it simple for you guys. For example, I have this Ca3, make it more simple. Then I will have this CH2 and then I will write this CH2 and I'm writing Br here, doesn't matter, okay. Elimination reaction mean when atoms or group of atoms they are removed from adjacent carbon. You can see it is alpha carbon because your function group is attached, Br is your function group, alpha carbon, and the carbon which is direct connected with this carbon is known as a beta carbon, okay. So what is the rule for elimination? Function group will remove from alpha carbon and one of the hydrogen will remove from this beta carbon. So you will, it is removing from here, okay. So you will get a double bond here. So now you will get this number one, CH3. I'm writing this CH3 single bond with C, this H, and double bond. It is CH, and now it is the double bond with the CH2, CH2, and it is your inorganic product HBr. Okay, when there is alcohol, so it will follow elimination reaction. How to define elimination? When atoms or group of atoms remove from adjacent carbons and they develop a double bond. This reaction is known as elimination reaction, okay. And what is the principle of elimination reaction? Functional group remove from alpha carbon and one hydrogen will remove from a beta carbon, okay. alpha carbon by which your functional group is directly attached. And the carbon which is direct connected with alpha carbon is known as beta. It is not beta, it is gamma, alpha, beta, and gamma. Okay. So it is a type of elimination. So what is the like inorganic product? You can say it here like NaBr, HBr, even you can say water. Okay. H2O, because we're using NaOH, that is why I'm writing here NaOH. Okay. Even you can say it HBr. Okay. So the next question is, so we have this question. Question number 4. Compound G and K are found in plant oils. Okay. Aldehyde group and it is ketone. Carboxylic acid group and carbon to carbon double bond. It means it has some alkene. Complete table 4.1 to state what you would observe when J react with the reagent listed. Okay. So we have this 2,4-dinitrophenyl hydrazine. So we use this reagent when there is a carbonyl group. You know, carbon carbon double bond. This group is known as a carbonyl group. It is known as carbonyl group. And carbonyl group is available both in aldehyde when there is C double bond O, and this direct connected with hydrogen aldehyde, and it also react with a ketone. What is ketone? And C double bond, both sides are connected with any carbon. Okay. So is there any aldehyde ketone? Here we can see it is a ketone group. You can see this group is a ketone. It is a carbonyl carbon connected with this carbon and this carbon. So complete what you observe when J react with reagent. It is a J react with. So what is the precipitate of this? So now we need to write their precipitate color. Okay, so we get this yellow precipitate. We will get this. When aldehyde ketone react Brett's reagent, it is known as Brett reagent. Okay, Brett's BRED Brett's reagent. Okay, so yellow precipitate. We will get this. What is a tolerance reagent? You know, tolerance reagent only reacts with aldehyde, but it doesn't react with ketone. So here you can see I have this aldehyde group. It is actually C double bond O, and with one hydrogen is here. Because of this, the tolerant reagent, okay, it is also known as a silver mirror test. So what are their like observation? We will get this a silver mirror. Okay, we will get silver mirror on test tube. Okay, sodium metal. We have one alcohol group as well as we have this carboxylic. You know, single sodium is highly reactive. Okay, single sodium can react both this part and this part. Okay, so when there's a sodium react with OH, for example, we have this alcohol ROH. It is reacting with sodium metal. Sodium displaces hydrogen from here. We will get a salt O negative, and sodium will displace that hydrogen plus a hydrogen gas will remove from here. Okay, so when the hydrogen gas will remove from here, we will notice here some fizzy or effervescence. Okay, this observation fizzy or hydrogen we use only for two gases. Number one, carbon dioxide, and number two for hydrogen only. Okay, J has two optical isomers. Draw the three-dimensional structure of two optical isomers of J. Okay, so one of the side is with aldehyde group, other side is ketone and OH. Okay, so optical mean now we need to draw the mirror images of each other. Okay, so here I can say we have this central carbon and one of the end, you know, connected with OH, and here we will have this C double bond O and CH3, and you can write this end with this means this is a wedge. Okay, it means when come outside out of the plane, when something is coming outside the plane, then in chemistry we use this type of bonding called explaining three-dimensional structure. Okay, so here we have this CH3 and this side we have this. Okay, so when I'm writing this type of structures, this hashes, it means it is something which is coming beyond, like behind that mirror, okay? Plane, sorry, not mirror. So now I'm like writing, now I will write this O will here, then H opposite of this, and C, okay? So it will become like this, okay, from bigger to lower, understand? Then OS, they are mirror images of each other, okay? And here I need to draw some opposite of this, CH3, and then C double bond O, it is CH3, okay? Or mirror image of each other. So I think it is the last question or no? One, two, three, four. Oh, we have only 3 pages left. So we have this next question. K is used to make the addition polymer perspex. What is the perspex use? Your car windows, okay? Windscreen, the first screen of your car. This is not a glass. It is actually a polymer perspex, okay? A synthetic perspex is shown in figure 4.2. Here we have this carboxylic acid and here we have carbon to carbon double bond. In reaction 1, this carboxylic acid is converting into some ester group. You know, when a carboxylic acid react with alcohol, you will get this ester, okay? And rest of the thing is same. And what is happening here? This thing is in reaction 2 converting into perspex, okay? Identify L state condition required for reaction 1, okay? So here we have this carboxylic acid converting into alcohol, sorry, ester. So identify the L. So first we figure out what is this L, okay? Like what is this? So we can say it is C double bond O. You can see it is C double bond O, then O, and then it is CH3. It is CH3. For example, if I break this molecule from like here, if I break the molecule, I will get this C double bond O, and it is a positive carbon. It will attach with negative OH. Carboxyl plus, I will get this HO methanol, okay? So this L compound is actually methanol, CH3OH. And what are their conditions? You know, we use sulfuric acid, okay? We will use sulfuric acid as a catalyst plus heat under reflex. Heat under reflux, okay? For this, okay? So draw one repeat unit of addition polymer perspex. We need to, here we can see one of the end is like this ester, but there's no other side we can see, okay? Like there's no other function group, so we can combine them together. So here we have this C double bond. It means is a type of addition polymer. Is a type of addition mean now we need to break this double bond, okay? So we will draw this carbon to carbon, and this side is connected with this ester, okay? And the lower side connected with the Ca3, and this side we will have this hydrogens. It is a one repeat unit, okay? Understand? So you can connect further. Use information from table 4.2 suggests how then from respect of M and perspex would differ. Okay. And M, we are talking about this and we are talking about this. So you can notice here we have double bond and if you don't have any double bond, okay? So now we need to figure display, okay? And what about here we have carbon to carbon double bond. Here we also have this same group, but difference is double bond and single bond. And what is about the double bond? Carbon to carbon double bond here. And this is from 1500 to 1680, okay? 1500 to 7 to 8 means this M will have double bond. M will have carbon to carbon double bond. Will have double bond. between carbons, okay? Carbons. So now their peak will be around 1502, and they show absorption at 1500 to 1680 to 1680. Okay, neither no. So now we have this next one. K can be made from propanone in three step. Here we have this ketone because this carbonyl carbon direct connected with carbon this and this. When carbonyl is direct connected with carbons, it is a ketone, and ketone is converted into this CN. Is a type of like when you have this HCN, like when you have this H and C triple bond N, this CN actually it will behave. I'm just removing this. It will behave as a nucleophile. So it will attack over here, and pi bond will become here, and you will get this CH3. For example, I'm writing it here. CH3 carbon double a single bond oxygen, and here, and I will have this CH3 here. Okay, so next C triple bond N will connect here, and now if you have another molecule of this HCN, so this oxygen will extract this hydrogen, and you will get again this attacking nucleophile. Okay, so you will get the final product like this, CH3 carbon with OH, with this CH3, and here we have this C triple bond N. So it is the product. Okay, now understand the mechanism of step 1. Okay, now we have step 2. This nitrile, when this nitrile group undergo hydrolysis, we get this carboxylic acid. It is actually when H positive plus water. Acidic hydrolysis of nitrile group. This group is called nitrile group. Okay, nitrile. Okay, and rest of the molecule is same. And here we have this. You can see double bond. Okay, so how to write this double bond? Elimination reaction. What I told you about elimination, I told you. For example, we have this C and CH3. Okay, CH3, CH3, and then we will have this C with this OH, and here we have this CH3, and here we have this C double OH. You know what is elimination reaction? When it is alpha carbon, because your function group connected with this carbon. It is a beta carbon. It is also a beta carbon, okay, because it is also connected with alpha. So OH removed from alpha and one hydrogen removed from beta. So when elimination is there, so you will get this product, okay? You will get this and this, okay? You will get this product, okay? Elimination reaction. So complete the table 4.3, identify the reagent, use and type of reaction. I already told you, you can see it here, HCN or NaCN, okay? Whatever is in your book, you can see, okay? So we will use this HCN as a reagent, okay? So catalyst is NaCN. KCN or sodium cyanide is your catalyst. A deadly catalyst, poisonous. Cyanide is really deadly, okay? And what is it? Is a nucleophile. There's a negative charge, nucleophile attacking here, and bond is broken. So it is a nucleophilic addition reaction. Okay, type of reaction is nucleophilic nucleophilic addition reaction. Okay. Okay, second type of reaction is, you can see it is being hydro in the presence of this H positive HCl in water. It is a hydrolysis reaction. Okay. Even you can say like H2SO4 HCl. Okay. plus water, aqueous condition, aqueous hydrolysis, okay? Please check your book. In my mind, it is HCl as well, okay? Aluminum oxide, it is a type of elimination, but I already explained you, okay? It is an elimination reaction. Elimination reaction, okay? And the next is, okay, I have done this.